Assalamualaikum warahmatullahi wabarakatuh, and hello everybody. This video is the continuation of the previous video, which is still under planar kinetics of a rigid body, force and acceleration. The previous video is all about the overview or introduction of this chapter, but today we are going to discuss the first subtopic or first subchapter, which is mass moment of inertia. Right. Basically, if you see before we go to a mass moment of inertia itself, I want to introduce some basic understanding of why mass moment of inertia is important. Alright, if you have a block here, block A, I name it as a block A, and this is a block, same block, block A as well. And these two blocks are identical. Assume that this guy push the block A to the right for the amount of force, for the example 100 Newton, and this guy as well push the block A to the left for 100 Newton as well. So we can say that this block is in equilibrium position, which is it doesn't move to the left or to the right. Okay, but let's say this guy push the block for about 50 Newton to the left. So we can say that this block has a motion to the right, correct? And then it moves linearly to the right because it will have a V and it will have A. Alright, so it has a linear motion. You can say that the summation of force, if we use the F, summation of F is equal to MA. So first we ignore the friction force. So the summation of force in X is equal to MAX. So to the right is positive. So we can have 100 Newton minus 50 Newton and MA times A. Since it experienced a linear motion, we can say that the force acting on this block A is concurrent force, because the action of these two forces is in line or cross the same point. Alright, it cross at the same point. We can say that these two forces acting on the same point. So you have 100 Newton here, 50 Newton here. Alright, so it will have a motion to the right, but since it acts on the same point, so it doesn't create any rotational motion. Okay, but when we go to the second figure, the same block A, alright, pushed by this guy for the example 100 Newton. Alright, so we have a blockage here, so that it or stopper, so it will stop this block A from moving to the right. So what happens when this guy gives 100 Newton force to the right? So when this one doesn't move, so what happens? This block will tip over. It will tip over. So we can say that the action of this force 100 Newton is to the right at this point, and this blockage also create a force to the left. So these two forces doesn't act or doesn't cross at the same point of action. So we see that. So since it has different amount of force, we don't know here, but it has amount of force here, for the example 20 Newton. So what happened is it will create a moment. Right? So once it creates a moment, it will experience a rotational motion. This force, since it doesn't act on the same point, so we call it non-concurrent force. And the first one, we call it concurrent force. Alright, so I hope that you understand this basics of important to know the concurrent and non-concurrent force. Alright, we go to the next uh, I mean notes, which is what is a mass moment of inertia, right? Basically, we define the moment of inertia as the integral of the second moments about n axis of all the element of mass, dm. You have a few masses here. Take it as a dm for the example, and then which compose the body. So every single elements or masses here, when you compose it, it will create a one single body. Sorry. It will create one single. The combination of many small mass here will create a single a single body. Right. Mass moment of inertia is given as I is in the integration of r square. R square means r is the radius from the axis of rotation. This is the axis of rotation for the example. R is the distance from the axis of rotation to its mass. Alright. So we integrate it with respect to mass. Alright. This is the equation to represent it. And then we know that mass is given as rho times V. Alright. So instead of M, we can replace dm as a dV, because when V change, M also change. Alright, but rho is fixed. It's nothing to do with rho. So instead of M, we can change it to the integration of R square rho dV. Now this one is V. Okay, so we can put the rho outside and remain R square dV. Okay, this is the equation to represent the mass moment of inertia of this small mass. Alright. Okay, when the volume element chosen for integration has infinitesimal dimensions in all three directions, we know that rho v comes from x times y times z. So these three variable can change either x, y, or z. Alright, so or in other way we can say that it is not written in the books, but I will show you. This is how we, sorry. So we integrate it, triple integration. First, of course, with respect to x, or second one y, the third one is x. R squared. So you integrate this one with respect to x, respect to what? Another one? y and the z. But we can simplify this equation. We can simplify this equation so that we can make it as a single integration, provided the chosen volume element has a differential size of or thickness in only one direction. So we can take it as a one. We fix two elements, for the example y or z, and the changes element is only x, for the example. All right. To solve the to find the mass moment of inertia, we can solve it through two type of differential elements. First, we call it shell element. Shell element. Okay, if you see this, it's not here. Basically, shell element. So try to imagine that you have numbers of shell. Numbers of shell. For example, you have first shell here. And then you have another smaller shell. Here, for example, you have R. Here you also have a shell as well. But the R here is smaller. Let's say this one 2. This one 1. So R2 is smaller than R1, for the example. If you slot this shell element inside this first shell, what happens is you will have two layers. It become a composite bodies. This one, the first one. Sorry, the second one. Now you have another layer. So end up when you have a several or many shell element, so you can create a rigid body. For the example, it become a cylinder. Okay, shell element also can be used to determine this kind of shape, right? So basically, from the previous equation, this one, the shell element can be the volume for the shell element can be represented by dv, right, is equal to 2 pi y times z. 2 pi y times z, and then you have the dy, right? You have the ty. Okay, this element can be used to determine the moment of inertia, for this one, right? About the z-axis, since the entire elements, due to its thinness, it's very thin, lies at the same perpendicular distance r. It lays from same r from the z-axis. How do you get? First, I want to explain to you this one. How do you get this one? Maybe you can, if you read the book, maybe you it's difficult to find it. How to find 2 pi y times z? Basically, this element, this equation is representing the volume. So take this element, right? Take this element and you cut it at one point, long this z or height. Once you cut it and you open it, when you open it, it looks like a paper, correct? It has a thickness and it has like a paper, but it has a thickness like a plate. And then here we can say that this length is what is the parameter for this shell. the perimeter. Perimeter can be found using the equation of 2 pi r, correct? 2 pi r, or if this one we call it 2 pi y. This one y, because this one sex, yeah, similar to this one, you have y. Okay, 2 pi y. The height itself is z. Okay, and the thickness here, you see that the thickness here, the thickness here, the thickness here is dy. You see that the thickness here is dy. Thickness d, sorry, dy. That's why you can find the volume for this one is as 2 pi y times x times dy. Alright, that's one for the shell element. When we go to this element, dv for this element, see the shaded one is written as how? Pi y square. Y square. Y is the radius basically. Where the radius for the this element. Sorry, this element. Right? Pi y square times dz. Alright, this is how we get the volume of this element. Alright, so this the two elements is the basic uh, uh, element that normally be used uh, to calculate the mass moment of inertia of any ship. So for the next video, basically I will explain to you how we are going to solve some sort of a rigid body like a cylinder and so on using this kind of these two elements, inshallah. Okay, see you again next time. Thank you very much for watching.